And in this live class, let's look at this topic, continue from where we stopped on circle geometry. Now we've looked at some theorem already. From the first theorem, we have the angle at the is twice the angle at the circumference. So if this is center hole, angle subtended by a chord or an arc, let's say this is a chord AB, then this angle at the center, which is angle LB, is twice the angle at the circumference. We have two angles at the circumference and two angles at the center. So there is one angle up here at the circumference. There is another angle at the circumference at this side. So here, if this angle here is x, this is the corresponding angle at the center. And this angle at the center here will be 2x. That's what the first theorem is saying, that this angle at the center is twice the angle at the circumference. And also here, we have circumference here, y. Then center here, this is center to this one. So, which is a reflex angle AOB. And this angle here will be 2y. So that's the understanding of theorem 1 there. So, and this will help us to solve, problem that's related to this. And we have another theorem that follows this, theorem 2. When we have a circle, also center hole here, and we have a chord, let's say chord AB here. Now this chord subtend angle, if it's subtend angle at the upper part, which is the major segment here, all the angles subtend by this chord are all equal. Now, which means that if this angle is subtended by this chord, another angle subtended by this chord, then another angle here subtended by this chord. That is, we have three angles now, which is being formed by this chord AB in one segment. So all the angles in this segment are all equal. Now it follows from this first theorem here, that is, when we construct this, we join this to the center, join A to the center, join B to the center. Now this angle here is angle at the center, and if this angle at the center here is 2x, it means angle at the circumference here will be x, because angle at the center is twice the angle at the circumference. And also here, this is also angle at the circumference as well to this angle at the center. So which means here as well, this angle here also will be x. And also the same way, this angle here is angle at the circumference to the angle at the center here, and this angle too will be. Therefore, all these angles here are equal. So angle in the same segment are said to be equal. So it might be formed at this other part of the segment as well. And now we have another angle, number 3, another theorem from here. Also, when we have a circle with center hole and we have a diameter, diameter is passing through the center. Let's label it as diameter AB. The angle formed by this diameter in the circumference, on the circumference, this angle here is angle 90 degrees from the theorem. It follows from theorem 1 as well, which implies that angle at the center is twice the angle at the circumference. Angle at the center here is angle on a straight line. An angle on a straight line add up to 180 degrees. So this angle here is 180 degrees. And since here is the center and here is the circumference, so we just have to divide it by 2, and this angle therefore is 90 degrees. And when you see a symbol with 4 corners like this, it's saying that we have angle 90 degrees. So it means that angle in a semicircle is angle 90 degrees. And we also have another theorem, number 4. We have, when we have a circle with center hole, and we have a chord AB, and a line is drawn from the center to the chord. This line drawn from the center to the chord meet at angle right angle with this chord, and also bisect this chord. Bisect means divide this chord into two equal halves. So label this as N. This line drawn from the center now to this chord meets at angle 90 degree here with this chord, and also bisect this chord into two. That is, divide the chord into two equal parts. So that means the line AN will now be equals to line BN. So these are the two important things here. This angle meets at angle 90 degree. Now we can make a construction here by joining this O to point A and also join O to point B. And AO is a radius, BO is also a radius. Now we have two similar right angle triangles here, and when we solve for any of them, any side that's missing, sometimes we might be given the radius and we'll be given the length of the chord. And when we're given the length of the chord, that means when we divide by 2, we are going to have the length AN. And we might be asked to find the distance from the center to the chord. So by the use of Pythagoras theorem there, from Pythagoras theorem, we'll be able to get the missing side here. So now we have another theorem, number 5, and that has to do with a cyclic quadrilateral. We call something cyclic quadrilateral. That is a quadrilateral inscribed in a circle. And you know, a quadrilateral has 4 sides. A 4-sided shape that is inscribed in a circle is a cyclic quadrilateral. Now, when we have it, we have a circle like this, and we have a quadrilateral that is inscribed. 4 angles touching the circumference of the circle. That's what a cyclic quadrilateral is. So 4 sides and 4 angles touching the circumference of the circle. So we can label this as A, B, C, and D. So we have a cyclic quadrilateral ABCD here. Then the theorem is saying that opposite angle of a cyclic quadrilateral are supplementary. That is, in another word, opposite angle of a cyclic quadrilateral add up to 180 degrees. Now it implies that angle B here is opposite to angle D. So you can say angle B plus angle D is equals to 180 degrees. So that is what the theorem is saying. And also angle A is opposite to angle C. That is, we can say that angle A plus angle C is equals to 180 degrees. So we have this theorem as our theorem number 5. And also we have an extension of this theorem, which is exterior angle of a cyclic quadrilateral. That is, when we have a cyclic quadrilateral, we have a cyclic quadrilateral, a quadrilateral inscribed in a circle. Okay? Then, and one side is extended. We have this cyclic quadrilateral, and let's say this side now is extended, that is prolonged out. We call this angle here exterior angle, and the exterior angle of a cyclic quadrilateral is opposite, is equal to the opposite interior angle. Now, opposite interior angle is this angle here. So this angle, which is exterior, is equals to this opposite interior angle. So if this angle outside here is x, this angle here too will be x, because it's opposite angle of the cyclic quadrilateral. Now we can prove that applying this as well. Don't forget that if this angle here is A, for instance, we can establish that A plus x will be equals to 180 degrees. That's from this theorem, which is opposite angle add up to 180. And also, don't forget that here we have a straight line. So angle on a straight line also add up to 180 degree. So when we add this together, also a plus x here also equals to 180 degrees. Then which implies that from here we can conclude that here we have a is the same thing as a. Now to make it better, we can use, so far we want to prove, we can use another letter for a first and make it a plus b here, so that we can see what we are talking about. Then since a plus b add up to 180 degree, and also a plus x add up to 180 degree, so they both contain the same thing as a. That means a is equals to a here, of course. And for them to be equals to 180 degree, it means b also must be equals to x. So that is why b here is equals to x. That's why you can call this place as x. So exterior angle of a cyclic quadrilateral is equals to the opposite inferior angle. Now, these are the theorems that we have looked at, and which we're supposed to know, have it at our fingertips for us to be able to solve riders on circle theorems. And there are theorems on tangent theorem as well, which also are very important. So a tangent is a line that touches a circle at a point. So we have a tangent theorem. So when we see something called tangent, a tangent is simply a line that touches a circle at a point. So it has a point of contact at the circle. So that line is what is called a tangent. Okay. So it touches a circle at a point. This point here called point of contact. And this line drawn here is what is called a tangent. Now, let's have a center O here. Then, the first theorem we are looking at says the line drawn from the center to the point of contact is perpendicular to the tangent. Now, this line that is drawn here is, of course, a radius, because any line that comes from the center to the circumference is a radius. So you can say the angle between a radius and a tangent is angle 90 degrees. So this theorem is number one under tangent theorem. And when we apply it to solving problem, we can look at this problem here. We have a center and we have a tangent. So tangents can be drawn any part of the circle. It's not compulsory that it's under, it might be beside. So we have a tangent here this way, having a point of contact here at the circle, and a line is drawn here to the point of contact. So you have a line meeting the point of contact here, then another one like this, and this one is connected, and we are given this angle here to be 54 degrees. Now the question says we should find this angle called theta. Now how do we go about this? From what we know here, that this is the center, angle between the center, that is the line from the center to the tangent, angle between radius and tangent is angle 90 degree. That means this angle here, everything should be 90 degree. And we can easily say that theta plus 54 degree now is equals to 90 degrees. So when we take 54 degree, we have theta now equals to 90 degrees minus 54 degrees. And which implies that theta here equals to 36 degrees. So that is one application of this particular theorem. And there is another theorem on the tangent theorem. It has to do with tangent as well. If this is a circle and we have a tangent touching the circle at a point of contact here. Now here, it doesn't have to do with center. We don't need center of the circle here. There is a chord drawn from here to the point of contact. Now what we are examining here is the angle between this chord drawn and this tangent. So the angle between this chord and this tangent is now equal to the angle in the alternate segment. And the alternate segment here is this segment. So angle formed by another two chords that is attached with this chord. Now when we attach a chord to this chord, another chord to this chord, and they both meet here to form an angle. So the angle between these two chords formed is the angle in the alternate segment, which is equals to this angle between this tangent and this chord. So that is angle in alternate segment. So if this angle is x here, this angle too is x. So that's angle in the alternate segment. And the opposite also is true. So now, when you look at it from this side, you have this chord now as angle between this chord and this tangent. Also, it will be equal to the angle between the two other chords, that is angle in the alternate segment, which is this angle. And this angle is y, this angle too is y. So these are the theorems that we should know how to apply on circle. Now, let's look at one question to show this particular theorem. We have this circle given. Yeah? Kí wá ní tó ti send number. Mo busy mo ń bọ̀ bá ṣe ṣubú. Oh, sorry about that. Break in transmission. Now, let's look at the question very quickly here. We have, let's say this is a tangent at this point. Then we are given a chord. This chord on this side, and there's another chord here attached and joined together with this chord here. And we have another one here and joined together with this here. That is, we have, this is labeled as L, M, N, and this is R, this is Q, this is P, and we have this angle here between this chord MQ and this tangent, everything here at 60 degrees, and this chord, between this chord here, we have it as 45 degrees. And that's what we are given. And the question says we should find, number one here, we should find angle RMQ. And also, we should find number two, angle MPQ. Also, we should find number three, angle LMR. So these are the three angles we are finding here. And when we look at it, from what we have here, angle RMQ, where is it? RMQ. So angle between this line RM and RQ. Sorry, line RM and line MQ. So this angle here is angle we are finding, the first one. Then easily from here, we should be able to see something here. How do we get angle RMQ here? Yes, angle RMQ is the angle between these two chords. From here, that's angle RMQ. But from what we have here, this is angle given from here. And this is angle between this chord and this tangent. So when we look at it as angle between chord MQ and this tangent is 60. So this angle here too will be 60. Because that's angle in the alternate segment. So this is 60 degree here. Okay? Angle in alternate segment. And this RMQ we are finding makes these three angles to add up to 180. That is in triangle RMQ. The sum of angle in a triangle should be 180 degrees, of course. So that means when we add these two together, which is 105 now, and subtract it from 180, so we can say that number one, angle RMQ will now be equals to 180 degrees minus the sum of these two angles now, which is 105. And therefore, angle RMQ here is 75 degrees. So that's one way of getting it. Actually, we can see some other ways. Depends on the one we can see first. That's the beauty about mathematics and circle theorem. So the one we can see first determine the one we are going to find. Now, we have already gotten this at 75 degrees, which implies this is angle between these two chords. Now, I can balance it and get this angle here because everything on this line, LMN is a straight line, okay? And by the time we add everything together on that line, it should be 180 degrees. So now, if we are asked to find that angle, which I think we have to find it in number 3 here, so which is LMR, this angle LMR now. So we can find that first. LMR now, angle LMR is now same thing as 180 degrees minus the sum of these two angles, which is 135 minus 135 degrees, which means this will be 45 degrees. So that's angle LMR. Angle LMR is 45 degrees. And what else are we finding? Angle MPQ. From there, we have MPQ. Now, when you look at this angle MPQ here is angle facing this particular angle because it's cyclic collateral. We have MRQP, a cyclic collateral, and facing each other, opposite angle of a cyclic collateral. That means angle, that's number 2, angle MPQ is now equals to 180 degrees minus 60 degrees, which gives us 120 degrees, opposite angle of a cyclic collateral, add up to 180 degrees. So that is that. So this year we are come to the end of today's class. I believe you enjoyed this class. Support us here at Master T Maths class and subscribe to this channel so as not to miss out on our uploads. And also give a thumbs up and share this video. I appreciate your joining us and God bless you. Have a wonderful day.